All right, here we go. Probability of mutually exclusive events. Okay, so for this particular section, I'm going to just focus one time here. There you go, that's better. Mutually exclusive events, you want to watch out for when it's throwing dice, cards. That's all I can think of right now. But those are like classic ones. Dice cards, you're gonna have to watch out whether or not they're mutually exclusive or if there's an overlap. Okay. Two events are mutually exclusive, right? If they don't share, right? If they don't share any common elements, I hope you remember that from chapter 3. On a Venn diagram, there's no overlap. Okay, no overlap. That's another way of thinking of it there. Recall from chapter 4, we had to split questions into cases when two or more conditions have an overlap. Chapter 3, the same thing. And here's something I want to bring back from chapter 3. Okay, so you might think it's a little of the same here. That's true. So the number of elements in A or U, right? So A or U is both of the circles in this case, is NA plus NB minus intersection, right? So this is the intersection. Section, the elements that are in both, right? That's principle of inclusion and exclusion. If the events are mutually exclusive, okay, then the AND part is 0, okay? There's nothing in, like, if they were to overlap, there'd be nothing in there. So therefore, N of A or B is simply adding them up. Like this part right here is just dropped. Okay. So if you can say this, okay, this is for mutually exclusive events. That is the case. You don't have to worry. Don't worry about N of A and B. Okay, that's basically why that is just a short version of the original pi formula. How is this going to relate to probability? Just like, remember earlier we had n, everything was n. It works the same with probability. The probability of A or B is equal to the probability of A happening plus the probability of B happening minus the probability of both happening. Okay? Note, we use P here, okay? Not N. Right? That's the difference. That's the only difference between up there and down here, okay? If events are mutually exclusive, conditions or restrictions do not affect each other, we just have this one here, okay? And so they're very much the same, guys. It's just transferring it over to this unit where everything is about probability. Everything has a fraction or decimal percent. And we know that probability of both happening is 0. That's when we know events are mutually exclusive. Okay, so let's use a Venn diagram to read off the probabilities off of the Venn diagram. So we're basically going back to chapter 3 here. Okay. Given this Venn diagram here, how would you fill this in? Do you remember? Well, let's see if we can use our pi for 2 sets. What was it again? Let me see here. I will scrap this because it's, or let's make this a U. The number of elements in A or B is equal to the number of elements in A plus the number of elements in B minus the number of elements in both A and B, because we don't know if these are mutually exclusive. We don't know that. However, let's make an observation here. If I were to go 20 plus 40, that's already 60, right? If I add the 20 to it, that's 80. I have more than my universal. So I know I'm double counting, right? Just by observation, I know I'm double counting already. There's going to be something in here. But let's use this again. Remember this part, the OR? We go 75, but you never want to miss the fact that you have to subtract the outliers. So we're going to go universal minus the outliers is equal to A plus B minus, we call that X, right? The intersection. So 55 is equal to 60 minus X. You subtract 60 from both sides. Minus X is equal to negative 5. And so X is equal to 5. So that's one way of doing this. Make sure you have this on your study sheet. So this 5, I will use a pen for that. Right, this 5 goes in there. And once I have the middle, I just work my way out. Right, so this would be 15, because I go 20 minus 5 to get that. 40 minus 5 is 35. And now it's completely filled in. Every single section on this Venn diagram is filled in, so we're good to go. Let's just, I guess we know already, NU is 75. No surprises there. You can answer that. But now, I want you to notice that now it's all probability. So watch out for when you have a P in front, right? That's a probability. Probability. What's the probability of an element just belonging to A? Remember, this is A, not B. Do you remember that notation? A only. Let's rewrite it. Probability of A only. That's basically what that is saying. So we would say every single time we'll have this over 75, because that's our universal. And we go and look for A only. That's this one right here, 15. So it's just 15 over 75. Let's reduce that. 15 actually goes into both of them. Goes 1 over 5. You could write that as a decimal. You could write that as a percent. Sorry, it's a bit cramped there, I know. Should have made my first fraction a little smaller. Probability of only B, just that part, would be 35 over 75. Okay. Reducing that, 5 goes into both of them. That is 715. As a decimal, that'd be 0.4667, because you round it at one point, which is 46.67%. So what we're doing here is before in chapter 3 was always n, right? Just a number of elements. Just give me 15, just give me 35, right? That's all we would have done, but now we state it as a probability. That's all we're doing here. Probability of A or B, how would you do that? So you have to go 75 here. You have options here. You either add up these three, because A or B is everything in those circles, right? So you can go 15, 5, and 35, or you can go 20 and 35, you name it. So I'm going to go 20 plus 35, so that is 55 over 75, which is 11 over 15. It's a little small. I apologize for that, guys. Especially back row. 7333, which is 73.33%. Okay. So probabilities. What does this mean again? The A or B not. That would be your outliers, yes. Probability of being an outlier. That is basically what that is asking. So you have a couple of options. Think this through because I need you to have more than one way of doing this. You could we just take 73 away from 100, right? If we took this, because everything in the circles represents 73.33. Take that away from 100, you get it that way. You can just go grab the 20 and just put that over 75. That's 4 over 15, by the way. I'm not going to do the percentage or anything, or we could go 100% minus 73.33, and we get 26.67. Because it's the same thing as not happening. Remember the indirect? Someone sitting together, you do the probability, boom, you get 80%, therefore 20% not sitting together. Okay, it's the same idea here. I'm going to throw in some odds. What are the odds of an element being in B, being in here? So you have to think it's B. So we're talking 40. So we go 40 to what goes on the other side. You can do a bunch of methods. You can cover up B because you've used them up. So it's 15 and 20, right? Those two added together would go on this side. But I like to go universal minus 40. It's almost like your fraction there, or your there we go. 5 goes in there 8 times and goes in there 7 times. So if you want to reduce it, so it's not B only, it's just B in general. So some of these could be in A, we don't care, but we just take B all in general. Odds against A, watch that, it says against A. That means that not A goes first and A goes second. That's what that means, okay? And I tend to focus on the A first, like it happening. So you go up there, A is 20, and therefore on this side it'll be 75 minus 20. So it'll be 55 to 20. 5 goes into 55 11 times. It goes into 24 times. There you go. So this was just a bit of a refresher, warm up. I want to add, I don't know if I think I have room to do this here. Can I just, because you know this is going to go word problems, right? You know it's happening. It's inevitable. This is, let's rewrite this. If you have A or B, it's the probability of, how should I write this short and sweet here? Probability of something being in at least one of the two events. That's what that is saying. Probability of being in at least one of the two. I'll just leave it at that. The key word there is at least, being in at least one of the two. So there's a 73.33% chance that you're at least in one of the two. So it could be just here, in both, or just over there, but that's in at least one of them. Okay. All right. Go to 23. Oh, I wrote on this. Okay. Must have been bored. Okay. This is a side joke. Hope you stay awake. How's that? All right. A car company reports that for a particular model, car, I guess, 43% of the cars produced have heated seats, I always want you to think of a decimal as well, because sometimes the province says decimals, sometimes they do percentages. It shouldn't be an issue, all right? It's the same thing. Probability can be stated fraction, decimal, percent. Sometimes it throws students off. I just want to warn you. So how about you just write up the decimal right above it? 36% of the cars will have a sunroof, and 49% have neither, okay? I can tell you that this is a bit of a classic setup for whether or not something is mutually exclusive. All right, they'll ask you. The question will usually ask for it. When you read this, you're like, okay, I see what's coming my way. So that's the kind of your mindset. You should switch over to that. Are these events mutually exclusive? Show your work. Let's do that here. And I'll write this out. One way to check is to add everything. Add everything up. If it is greater than what? Your percent probability, right? Greater than 1 or 100%, regardless of, right? It depends on what you're adding. Events are not mutually exclusive. Because if it adds up more than 100, that means that there's something that you're double counting. There's an overlap, okay? So that's what that tells you. So let's check for that. So we'll go 43% plus 36% plus 49%. If you add that up, that gives you 128. I have to check that because I change numbers sometimes. Yeah, we're good. 128%. This tells us that 28%, okay, of cars have both, right? That's what that tells us. There's an overlap. Therefore, not mutually exclusive. That is like, you got to make sure you state that yet, right? Like you've done a pretty good explanation. Now you're saying, hey, it's greater than 100%. So definitely there's an overlap here. So we're going to draw our Venn diagram. It says find the probability of a car having both. We're going to do our Venn diagram. That's your best bet, right? What's my universal? It's probability. 100%. I'm off frame here. We know that, what are we going to call? We're going to call this H for heated seats. We know we have 43% in there. And we have sunroof, S, that's 36%. And we have 49 that have neither. So those are my outliers. Don't forget about the outlier. It's given, so that's pretty handy. I already did the both. I already know that, but if you ever run into an issue here, to figure out this, remember we're talking probability. This is probability of H and S. Always remember that. So we're going to go 100 minus 49. That is the universal minus outliers, is equal to 43 plus 36 minus probability of both, of a car having both features. So this is 51 is equal to 79 minus P of, let's just leave that notation as is. Let's take away 79 both sides. Just remember, these questions aren't always the same, okay? They're not always the same. So P of H and S is, now you slap on the units, okay? You gotta have it towards the end. So it's 28%. And I would strongly encourage you to then fill in your Venn diagram. So you go 28 here. Just found that. And you go 43 minus 28. That's 15%. 36 minus 28. That's 8%. So if they ask you any other question, you know how to answer it, right? Because chances are they will. Determine the probability of a car only having a sunroof. How do you write that again? Probability of sunroof, not heated seats. Remember? That's S only right there. And we're in probability territory, so we're going to go 8%. That's it. 8% of cars would only have sunroof. And I added D there. You didn't copy that yet, did you? So let's do that right here. I'm going to rewrite it for you because that's kind of sloppy writing there. What's the probability of a car having at least one of the features? What if the question read, what's the probability of the car having at least one of the features? It's asking for, find a percentage inside the bubbles, not the outliers. So you've got an option. You can go 100% minus 49. Remember the number of groups that have at least one grade 12er? You went all groups minus the ones that are not applicable. So that's 51% of cars will have at least one of the features. Or you could have just gone 15% plus 28%, right? 15 plus 28 plus 8. That's still 51%. So regardless of how you want to slice it, you still get 51% of cars. So that is the at least. At least is anything inside the sets that you're considering, the events, right? Heated seats versus sunroof. So 51 of cars will have either just heated seats or just sunroof or both, but they'll have at least one feature, okay? All right. Can I ask you, I'm going to take a little break from talking. I'll ask you to try 24. By the way, I could ask you for odds here as well. I'm just going to leave it for now. I think you're doing pretty good with odds. So let's try that one, and then we'll do outcome tables, rolling dice, all of that stuff, okay? So give this a try. I would say this for A. Just listen one more time. Showing me whether or not things are mutually exclusive. If you want to go ahead and make your Venn diagram and do a bunch of math and then show me, yeah, it is mutually exclusive. Look, I've determined that there's an overlap. That's good enough for me as well. Just show us somehow that you understand how to show it, right? You could do it graphically, mathematically. I'll start going over it. So appreciate you trying. School newspaper claims that 62% of students skip breakfast, 24 skip lunch, 22 eat both. So what's happening here? Because usually we have at the end, these ones have neither, right? That's what we're used to. Are these events mutually exclusive? So for A, how about we start with our Venn diagram? We've got 100% because it's probability, 62% skip breakfast. So you can call this B for breakfast, but these are skipping breakfast. These students are skipping breakfast, skipping lunch. Okay, so that would be 24%. 22% eat both. They actually have both of them, so they're not skipping. They're having, so in this scenario, they would be considered our outliers. Okay, outliers. So there we go. So you can perform a quick check, or you can just go straight into saying, hey, how many, the percentage of students skipping breakfast and lunch? Let's figure that out. So that would be 100 minus 22 is equal to 62 plus 24. I'm just going to call that minus x for now. I'm going to say, hey, this is x for me. So this would be 78 is equal to 86 minus x. And I think a lot of you had this on your minus, is it 8? Yeah, it's 8. Divide by -1. And x is equal to 8%. So I plug that in here. Subtract it to get 54. Subtract these two to get 16. So now everything is filled in. But you would definitely say events are not mutually exclusive. Since 8% of students skip both. Okay? They skip both. They don't have both. They're skipping both meals. So there we go. So for B, find the probability of a student skips breakfast but not lunch. So this is basically asking probability of skipping breakfast but not lunch. So that'd be 54% of students. There's a 54% chance that will happen. Okay. C, determine the probability of a student getting neither breakfast nor lunch. Okay, so that's actually asking for this. It's asking for, if you have neither one, it's the combination. So that's what they want. They want everything in here. So it's 54 plus 8 plus 16. So that'd be 78%. Or you could have gone 100 minus the outliers, everything else. And this is, if you read it carefully, it's neither breakfast or, so not having breakfast or not having lunch. That's how this is supposed to be read. It's not saying is getting neither breakfast and lunch, right? Like it's skipping both. It's either or. So it's, the or is referred to that. Let me see here. Should I'll just leave it at that for now. I have space for more, but I might do that tomorrow. Let's go over to 25. And I want to preface this. I gave you an outcome table to speed things up a little bit to get to the point, but I would expect you to be able to create one yourselves. Okay? So you have two 6-sided dice that are rolled together. So this could vary. You could have two 12-sided, 1 5, 1 4, it doesn't matter. So we want the probability that the sum is greater than 8 or multiple of 5. What? Right? So we want the probability of G8 or M5. I hope that makes sense. I'm just gonna write it like that for now. If it's two 6-sided, like imagine this is not here, right? Two 6-sided, you're like, okay, I have 6 options. and another 6 options. So that's 36 outcomes that I have to consider. That is something that I would expect you to catch right off the bat. 36 outcomes that I'm considering. Not 6 factorial, none of that, right? It's 6 and another 6. So here are your 36 outcomes. So you write out the combinations, 1, 1, 2, 1. So you just fill this in and you should have 36, right? Now, a sum greater than 8. Let's go and find that. There's a bit of a pattern. Okay, there's a bit of a pattern. How will I show this here? I think you will just have to bear with me. But watch this. If you add up 2 and 1, that's 3, correct? 1 and 2 is 3 as well. So this is like your sum of 3 line. You see that? Let's go over to this one. 3 and 1 is 4. 2 and 2 is 4. 1 and 3 is 4. So this is your 4 line. So there is a pattern. It's actually, right, 4, 1 is 5, 3, 2 is 5, 2, 3 is 5, 1 and 4 is 5. So this is your sum of 5 line. So I hope you can see that, okay? I might have to do another one where I actually show you that, okay? Like an outcome table with the sums. This one shows the outcomes, right? The possible roles you can actually have. So sum of greater than 8. Where is your 8 line? Find it. This is the 7 line. This is your 8 line right here. But you want greater than 8, correct? G8, greater than 8. So I'm going to grab a color, whatever you want to give G8. And it's along here. This is the 9 line. 6 and 3 is 9, 5 and 4, 4 and 5, 6, 3 and 6, those are all 9. So all of these sums right here, right? All those combos, and you can verify, go check, right? Because it kind of goes, this is the 2 line, the 3 line, the 4, the 5, the 6, the 7, the 8, the 9, the 10, the 11, and the 12 sum, right? So all of these roles will be greater than 8. Does that make sense? Okay, so G8 is there. How many outcomes do I have? So if it says or, we have to go like this. I'll do it one more time. G8 or M5. How many outcomes for G8 do I have? Because I need to add P of G8 plus probability of having a multiple of 5 minus, yikes, this has to fit in or else we're in trouble, probability of both. Can I just write that for now? I think that is okay. I have to consider that there's an overlap, and you're going to see it here. Let's grab a different highlighter. I'm going to grab green. Okay. Where are your multiples of 5s? Like where your sum is a multiple of 5. It would be 5. If you have a sum of 5, that would be your first multiple of 5. Okay. Where's the 5 line? Find it. It's right here, 4, 1, 3, 2. So this would be a sum that is a multiple of 5. Just like that. And the next multiple of 5, the sum would have to be, you're with me, right? 10, right? A sum of 10. Go find the sum of 10 line. I see it right here, 6, 4, 5, 5, 4, 6. It's right there. Do you see an overlap? You should. These 3 here have already been counted if you were to add the orange, right? So you see that these events are not mutually exclusive. So let's fill this in. I'm not going to rewrite this part. I'm just going to go G8 is, count, 1, 2, 3, 4, 5, 6, 7, 8, 9 outcomes. Hold on. Did I count that right? Yeah, it's 10, right? I think I missed this one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Thank you. So that's 10 over what? 36, right? There are 36 outcomes, always possible. Plus M5, it's also going to be out of 36, right? How many M5s? 1, 2, 3, 4, 5, 6, 7 outcomes. I need to subtract the instance where both of them are happening. How many did I double count? I counted these 3 twice. I added them in here and I added them in here. So I need to subtract these 3 from my calculations or else I'm off. Okay. Why am I doing the out of 36? Because this is probabilities. It's no longer number of. You're like, Mr. Erickson, can I just do like the number of first, like 10 plus 7 minus 3, and then just at the end slap a 36 under it? Sure, no problem. So all the same denominator, so 10 plus 7 is 17, minus 3 is 14 out of 36. Okay. I don't know if they're both even, I just divide them in half sometimes till I can't anymore. That's what I do. Like it's faster sometimes, and instead of thinking of what works. So there it is. Let's go get that as a decimal just in case we might need that. 0.3889, which is 38.89%. But 14 out of 36, I would have left it like that on a test or exam, to be honest, just in case you type it in wrong. So you could have said this, Mr. Erickson, I don't need this. I'm just going to go 10 plus 4, that's 14. I'm not going to do this. You don't have to. This is just showing you how this equation, this formula works every time. But these are not mutually exclusive. Not mutually exclusive events. And I don't know if you want to go arrow, but that is the reason, because it's found, it's being double counted. If you were to just go, we can't ignore the both. Okay, that's the main reason here. We cannot ignore that, or else we'll have the wrong answer. Okay, let's do one more here. I will ask you to try this one. Let's see if you can have some success here with that one. So imagine this is not there. You'd be making your outcome table, but now, so take like 30 seconds, like, okay, I'm making it, right? And then you start. What's the probability of getting a sum that is a multiple of 4 or a sum that's greater than 6? Oh, state odds as well. It did tell me that earlier. We're going to worry about that in a bit. Let's just figure out the probability. And if you're up for the challenge, go try 5 as well. Is this good? Is that what you got? Okay. Phew. Because I didn't have a key, so I had to like odds for and odds against. Regardless of which fraction you use, 4, let's do that first. That'd be 2, and then 3 minus 2, that'd be 2 to 1. This would be 4. Oops, can barely see that. 4 would be that. Against, you just flip it, right? So getting multiple of 4 or greater than 6, like getting those would be 2 to 1, and then 1 to 2 would be the odds against. Let's do a card scenario. So dice and cards, classic. Okay, you gotta watch out. It's like I would say it'd be pretty hard to do this one without an outcome table, in my opinion. And sometimes it's a smaller outcome table, right? If it's a 2 4-sided or a 4 and a 5-sided, it changes. So don't think it's always going to be out of 36, but most likely it is. Let's go to page 26 here, and we'll end with that. And this is where a deck of cards, I should have slapped the deck of cards on this page. Would have been nice. But so this one I probably leave that for homework, like whatever I don't finish on this page, and then there's some homework on at the bottom here for from your textbook. And then I have a list a couple pages after, which I'll just ask you, would this be mutually exclusive or not? I'm just asking you whether or not they are. You're not actually calculating, but that way your brain has to process that. What is the probability of drawing a red queen or a face card? Let's try that. Probability, let's go RQ or face. Like if you were to write it like that, maybe start off with saying, hey, I think I can figure out red. How many red queens are there? 2 out of 52, right? There are 4 queens, 2 of them are red. Let's add probability of just getting a face card. How many face cards? 12, correct? Out of 52. Is there a chance that I'm double counting? Because a red queen is also a face card. So you're already including that here. So I'm going to go minus 2 face cards, right? And I will try to explain that. So this is just 12 over 52. Let's try this. You've got Jack, Queen, King, Jack, Queen, King, Jack, Queen, King. Right? Half of them are red, half of them are black. We know that, right? So if you wanted to just have the red queen, these 2 here would be, if you go to the reds, it'd be these 2. Okay. Yeah, this works better than I thought. And then the face cards, like these 12, where they come from? Well, it's all 12 of them, right? You're including all 12 face cards. And you can tell that, hey, if you do the 12, if you add the 12, you've already included those 2. So I subtract the 2. So it's as if these 2 here never happened, right? It's really just 12 out of 52. Okay, so that's how card games. Oh, let's reduce this if possible. So that'd be 6 out of 26. That'd be 3 out of 13. There you go. Odds, it wants the odds as well. So I would actually, you know what I often do, you'll see that on my key. Instead of finding the odds, I first find a probability and then I turn it into odds. So if you wonder like what happened there, that's what I do quite often. So be 3, 2. You can't leave 13 there. You should be like, something is wrong with that. You have a number that is in the denominator here. Can't have that. So it's 3, 2, 10. Okay. Remember, if you were to add these 2 up, these 2 add up to 13, which is what you want, right? It is what you want. That is a bit of a check whether or not you're doing things right. Okay, I'm going to leave the rest. So I would say plus page 26 plus, I'm coming back to this page. Are you still copying? Where was it? Yeah, page 30, I made a list. So just page 30, even if you just do it in passing, like just looking at it, it's like I wonder, and I will post the key to that. And so there's not a whole lot of work on 26 left, to be honest. 30 is just look and see, and then we'll check out the textbook as well.